You are currently the only person in this conference.
Very good. Okay, so again, welcome everyone to this second lecture. So in the first part, we will, let's say, face problem of magnetostatics, and at the end, we'll touch the issue of units in magnetism, and also what has changed with the new international system. Okay, so magnetostatics. Magnetostatics, what do we mean by magnetostatics? Essentially, we mean that we take our Maxwell equation and we go in statics. So we do not allow anything to change in time. And you see there are variation in time of the magnetic induction in the Faraday law. There is the variation of the electric field in time in the fourth equation, the so-called displacement current of the Maxwell equation. This we put to zero, so we assume that nothing is changing in time. And then we are interested in magnetic field, so we disregard free charges, no? So we have no charges. Then the problem is enormously simplified. We only have to take the equations where there is a magnetic induction field, that is divergence of B equal to 0 and curl of B equal to mu 0 times the currents, the only source that we have. These are called the equation of magnetostatics. It looks simple, but this is a problem which is interesting enough to be treated. So if you take books on electrodynamics, they dedicate chapters on magnetostatic itself. What we do here is a big summary, no, of all these things. So we will touch essentially, without deriving the results, how we can solve the problems where we have a magnetic induction field generated by certain sources that are the currents. So at the moment, we don't care if these currents are microscopic in origin, let's say current loops at the atomic level or macroscopic current. The important thing is that they are fixed. So we know what is the current distribution in space, and we want to know what is the consequent magnetic induction field. How can we solve this set of differential equations? Because there are six, no? We have six differential equations. Sorry, we have four differential equations because the first involved a scalar. And so it's not that easy to solve the problem as it is. So how it's possible to solve a problem like this? Well, first of all, we have to add one thing, the fact that the current are stationary in time. So not only current is fixed, but also the divergence of the current is equal to 0. What does it mean? This equation means that you have flowing current somewhere, but the electric charge does not accumulate anywhere. No, so you don't have capacitor or things like this where you may have accumulation of charges. This is impossible. So this equation that you see there is simply one part of the continuity equation for the charge, where the derivative of the electric charge density has been put to 0, because we have said that charge is 0 everywhere. So this is an additional and important condition to have. How to solve this equation of magnetostatics? Well, we can do the following thing. Well, the first, we have the divergence of the B field is equal to 0. The second is the curl of B is equal to mu 0 times mu 0 J, where J are the current densities. Well, but the fact that the divergence of a vector field is equal to 0, we can always assume that the B field is equal to the curl of another field. In this way, if we make the divergence of a curl we have 0. So the first equation is always satisfied. This vector A is called the magnetic vector potential. You find it in treatment of electromagnetics everywhere. Here I use a few relations of vector analysis. So if you put the curl of A into the second equation, then we find something which looks a little bit complicated, which is the curl of A. Well, we have to know we have to know this analysis for the vector field to know that this can be simplified. And this can be simplified in terms of what is written here. So that complicated thing can be written as the gradient of a scalar, which is the divergence of A, minus nabla square of A, or the vector itself. So second derivatives of the vector A. But then there is still something to fix. No? So in electromagnetism, we have always some degree of freedom, as we have introduced this vector A as the B as the derivative of something. We have something to fix of this vector A. And this freedom is called the gauge. This gauge freedom is something that we have to fix, and somehow arbitrarily. So if this is an arbitrary condition that we can fix, then we fix what is called the Coulomb gauge. So we choose a vector field whose divergence is exactly equal to 0. This is the gauge which is chosen in magnetostatics, essentially. If we do like that, then the magnetostatic equations are much simplified. We obtain the nabla square of A equal to minus mu0 times the current. What happens? It happens that we have a much more simple equation to solve. This equation, when we have second derivative of a vector field equal to another vector, is called a Poisson equation with sources. So we know already that electric current are the sources of the magnetic induction field, but then here we have an explicit equation, a Poisson equation for the vector potential. Well, everything looks very formal, but the important thing is that this kind of Poisson equation can be immediately solved. So we start directly with the Poisson equation for the vector potential, and we write the solution. This is the formal solution of this Poisson equation. Again, I'm not demonstrating anything, so I'm taking the results from electrodynamics. The vector A, the vector potential, can be simply computed if we know the distribution in space of the current. So there is a weight, which is 1 over the distance between the point where you want to compute the vector potential, so point R, and the point where are the sources, R prime. This integrated factor multiplied by the current and integrated over the whole space, and then we have this multiplying factor and this 1 over 4 pi, gives the vector potential. Immediately, if we take the curl of the vector potential, we compute magnetic induction. And this is the equation which is written here. It's quite a complicated integral if you look at it like this. But do something, let's say, very simple, no? So instead of letting the electric current density to be anywhere in space, you can, for example, consider that the electric current is flowing through electric wires, for example. And as we know, the divergence of the current is equal to 0. So this means that the electric current will be continuous through a certain wire. If we do like that, instead of integrating over the whole space, and if you take a circuit, an electric circuit with a wire and a constant electric current which is flowing through the wire, from this quite formal expression, you obtain a quite well-known equation, which is the Biot-Savart law. What we have done there, we have hypothesized that the current is flowing only in the wire, And at the place of the vector j, we have put the vector which is pointing along the circuit, and then we integrate along the circuit. This is the magnetic field, the magnetic induction field, which is generated by the current I, which is flowing through a wire. Well-known Biot-Savart law, magnetic induction field generated by current-carrying wires. So we arrive at something that we learn in Physics 2 books. Okay, this is very nice. And what can we do next? We can do something that, let's say, in a sense, was missing in the previous lecture. So it's quite common that this distribution of currents are concentrated in a certain region of space. And we want to observe a field very far from that region. So the question is the following. If I have a solenoid or a current loop or a system with current which is generating, that is a source for the magnetic field, for the magnetic induction field, if I go very far from the source, can I derive some general properties of the field which is generated by this source? Yes, and this field, this far field, is called a dipole field. What does it mean? Well, it means that the particular arrangement of the current that you have in your generator, so it can be a current loop, a solenoid, or just a mess of wire, it doesn't matter too much if you are very far from it. So we want to understand what is the quality, no? What is the quality of the arrangement of wires that matters for generating the field far from it. How can we do this? Well, first we take the solution for the vector potential, no? The general solution. But then we make the hypothesis that the electric current density is concentrated in a region that we call omega. So R prime is the position of this current density. This current density are only concentrated inside the region omega. We don't look at the potential inside the region itself, but we go very far from it. So suppose R is the coordinate of the point where we make the observation, and R minus R prime is the distance between the point where we make the observation and the sources. So R prime is limited, no? So it's limited in this small region. This means that we can make a series expansion of the terms that we have there. We have to compute the series expansion, and then we find several terms. The first, the second, the third, and so on and so on. We limited the first two. So the first is just 1 over R of the integral of the current over the volume where the current are concentrated. But if you think about it, we have already hypothesized that these currents are not accumulating charges anywhere. So if you integrate over all the volume, this integral must be 0. So the current is going one direction in one side of the region and the other direction in the other, like a current loop. So the total integral in that volume where the current is limited and it doesn't go outside. So imagine that inside the region omega, you have the generator and the solenoid, for example. The integral of the current density on this region is 0. So this first term, the 0 order term, is not present, is equal to 0. So in order to understand what is generating, what is important, the first non-zero term, we have to go to the next. The next one is 1 over R3, and then it contains this product, distance times current densities. If we rearrange this term and we write just the contribution of these terms given as a result the vector potential A, we write this nice equation of having the vector potential A equal to the external product of a quantity that we call mu, external, the distance, divided by the distance to the third. Mu, we define mu as the magnetic dipole moment. Very nice, because if we take just this equation here, it tells that we don't need to know every detail of the distribution of current if you stop at that power of the expansion. We need only to quantify the magnetic dipole moment of this distribution, and then the rest is just a distance. This is exactly what we had in mind at the beginning, to identify a quantity that is responsible for the far field behavior. The first term which is responsible is called, it's the dipolar term, and the quantity is called the magnetic dipole moment. How can I compute the dipole moment? This equation is written here. I have to take the distribution of currents and so on, but the result is a number, no? It does not depend on in space. It's a property of the volume. How to say, it's an integrated value. If I take a region which is double in size, then it means also the magnetic dipole moment is double. So it's an extensive quantity in terms of the physics. It describes how, exactly this, the magnetic dipole of the region. So this magnetic dipole is extremely important if we only want to know the field very far from the region that has generated. The results of this field generated by the dipole, so when we go very far, it's called dipolar field. Take this vector potential A, take the curl, and then you end up with the expression of the dipolar field, which is written here. Quite complicated, eh? So the magnetic dipole moment is a vector, and then we expect something different for the magnetic potential, which is for the magnetic induction, which is generated in the same direction of mu or perpendicular to mu, and also there will be a dependence on the angle formed by the position and the magnetic moment itself. To understand a little bit more, we can make a drawing. So, for example, we can draw the magnetic induction field generated by a magnetic moment, a magnetic dipole moment. So, in the picture there, you find exactly the drawing of this. What you have that's in the origin of this plot, we have a magnetic moment with direction pointing to the right. Then we have both red lines and gray lines. The red lines are the so-called field lines, while the gray lines are the so-called potential lines. So if you put the field lines have the following properties. Along that field line, the result, so the magnetic induction, is parallel to the line itself. The potential lines are lines where the energy is the same, or the energy is the same. The potential is the same. The vector potential is the same in this sense. So it happens something quite important for the dipole field. Put yourself at a given distance from the moment, which is at the center, and then turn around it. You will find that the field that you find when you are in the direction to the right is one value. But then when you make 90 degree in counterclock motion, then you will find that the magnetic field points in the opposite direction, and this modulus is just 1/2. So this is the dipole field that you find in many books or whatever, in many situations. Static, no? Static generated by a magnetic moment, constant, and put there. Okay, so let's say we have done in this case the hypothesis that the volume where the sources are is just concentrated in one point. So we never go, we are always in the condition of the dipolar field. Okay, very interesting, but this is just one point, and it's not the case that we have in practice when we want to study magnetic materials, in practice or in theory, because magnetic materials are extended, so they are not points. And also, if I consider a piece of magnetized material, I cannot just simply sum up contribution of this kind, of single dipoles. It's much more complicated. And then you're exactly in the condition we said before. Hopefully, you can also want to compute the magnetic action, the magnetic field, as we will see, or the magnetic induction that you have inside the material, not only outside. So the magnetic dipole, it was good as an exercise, but then if we want to understand something more regarding, or if we want to treat ferromagnetic material or magnetic material in general, we have to solve a problem which is more general. So what we want to do now is to take again the equation that we have derived in the previous lecture. That is the Maxwell equation in the matter. So we want to consider explicitly magnetized matter, and then to derive equation for the magnetostatic field. So let's start again from the beginning. And why do we start again? Because we have not the same set of equations. So again, we consider that the time derivative of equal to 0. Again, we disregard any charge. So we don't care about the Gauss law, we don't care about the Faraday's law, and so on. And also we put the displacement current equal to 0. But now we have one equation for B and one equation for H. So we have to find a different set of equations now. And remember that now J, the electric current density, is just one part of the source. These are only the source, the current that I control. But there are also magnetic materials now. How can we do with this? Well, yes, exactly what I said now. So take again these two equations, but we have one equation for the magnetic induction and one equation for the magnetic field. So what to do? Well, first, let's limit to the case which is opposite to let's use the relation with B and H that we have derived before, because we had divergence of B equal to 0. But let's suppose now we have magnetic materials. So we know that P is equal to mu 0 H plus mu 0 M. So let's use this equation in the first, and let's derive then these two equations. Now we have not anymore the magnetic induction field, but the magnetic field H. So we have to solve for H. And we expect this because now we have magnetic material. So it's H that we want to deal with. But then the first, that at the beginning was equal to 0, is no more equal to 0, is equal to something, is equal to minus the divergence of the magnetization field, while it remains an equation which is curl of H, which is equal to the current, where now we have only current that we can generate. So the situation is exactly like in the picture below. We have two kinds of sources. One, which is the same as before. So the current, the field generated by the current that we can generate by means of solenoids, by means of loops, or whatever. So we need a current generator, we need some current flowing through some conductors, and so on. But we have also magnetic materials. So we have matter which is magnetized for reasons that is not completely under our control. And if we think about it, this picture is exactly the situation where we always are. So this is a situation where a transformer works, where we have magnetic materials and we have windings around it. The situation where we have an electric motor is a situation where we have a magnetic material that we want to measure, and we want to apply a magnetic field in order to change the magnetic state, we are always in a situation like this. For some reason, we have some action generated by us, which is under our control, for example, by this current, and we have some counteraction of the magnetic material itself. So this is extremely important to consider, and it can never be disregarded in a sense. What to do if we have two contributions like this? Well, it means that the shape of the magnetic field when we have magnetic material is much more complicated than the magnetic induction where we have only electric current as a source, so the ideal case. Let's take this specific case. That is, we have a piece of magnetic material and we want to compute the magnetic field generated by it. So we don't introduce anything externally. This is just the magnetostatic field generated by the fact that this piece of material is magnetized. And you write it this way. So I've added the subscript M to remember that the sources of this magnetic field is only the magnetization. Well, but if you look at this equation looks extremely similar to other equation, that is the equation for the electric field. So the curl of HM is equal to 0. We have no currents. All the sources have been put into the magnetization. Then we can do a lot of very interesting things. So, for example, as the curl of HM is equal to 0, we can introduce a scalar potential exactly in the same way we do with the electric field. We are allowed to say that instead of the vector HM, we want to deal with a scalar, which is this potential phi m. And we just say the magnetostatic field is nothing else but minus the gradient of this magnetic scalar potential. And then we follow something which is in the same line as before. We take this magnetic scalar potential, we put into the first equation, and then we derive, we find that we have a nabla square of the scalar potential minus a scalar, equal to minus a scalar. And this scalar is the divergence of the magnetization. But in the corresponding Poisson equation, this looks like a charge. It's exactly the same kind of equation that you find when you solve for the electric field generated by the charges. So in the end, what do we have? We have that we solve an equation in presence of magnetic material and nothing else. We can solve a differential equation for a potential. The charges is the divergence of the magnetization. And that's it. But for this Poisson equation, again, we have a formal solution. But we remember one thing, that this is different from before. We remember that this magnetization is not everywhere. So we consider that we have magnetized material inside the volume V and nothing outside. So the formal solution is written by separating a term which is an integral over the volume and another term which is an integral over the surface. So if you work out this, you will find that the term which is integrated over the volume still depends on the divergence of the magnetization itself. So the derivative of the magnetization, where the magnetization changes in space. But the surface term is just the change of the magnetization at the surface. So, for example, in a piece of a ferromagnet, at a certain point, when you arrive at the border between the material and nothing else, air, for example, you have the projection of the magnetization vector times to the normal. This what means this? That you have substantially two sources for this magnetostatic field. One that comes by the fact that the magnetization is non-uniform inside the material, and the other that comes from the fact that the magnetization goes from the magnetic material to nothing else. One is surface and the other one is volume. You can easily put to zero the first if you are able to have uniform magnetization. So suppose that you have a body, a sample, where the magnetization is uniform. Then the first term is equal to zero. But you will never be able to put the second term to zero. And you will always have a contribution from the surface. So please keep in mind that this magnetostatic term from the surface you cannot eliminate if you are working with a finite sample. That is most of the cases. Well, these two contributions in the books of magnetism are sometimes called the stray fields and the demagnetizing fields. So these are things to remember very well. The contribution from the volume, so the fact that the divergence of the magnetization is non-zero inside the material, contributes to stray fields. The fact that the magnetization passes from a certain magnetization inside the material to zero outside is called the magnetizing field. This demagnetizing field, both are extremely important, and we will return to this magnetostatic field in several lectures in the following. So remember this quite well. Yeah, if you like, yeah, you can put together the two views of magnetostatics in the picture that is at the right hand side. So take a piece of a cylinder of magnetic material, and imagine a magnetization which is pointing along the axis of the cylinder. If you remember the first part, we just said that we can compute the magnetic induction field generated by the current. And in the introducing, in the first lecture, we also said that magnetization corresponds to magnetizing currents. So if you just consider magnetizing currents, your magnetization of your cylinder will be a distribution of currents at the surface of the cylinders. And the magnetic induction field is just the result of this distribution of this current, which is flowing at the surface of this cylinder, if you like. But if you don't like this approach, you can think exactly in the way that I described here. So instead of magnetizing current, you can think of surface poles. So consider the magnetization uniform, the divergence, the change of the magnetization is only at the upper and lower surface. In that place, it's the only place where these magnetic charges are present. No, these surface poles, no, could be called. So it's like the description is exactly the same of a charge capacitors, and the consequent field, H field, can be derived by the equation that we have shown before. The difference between B and H is only inside the material, because outside they will be the same. Magnetization is zero. Only inside they are different. And this difference is important because if you think about it, it means that the magnetic induction B is pointing in the same direction of the magnetization. No? If you take these currents shown there and use the rules that the right hand, you get a B which is pointing up. But for H is the opposite. The magnetic field that is generated by the surface poles goes in the opposite direction inside the material. This is the reason why it's called the magnetizing field. Inside the material, the magnetic field generated by the magnetization itself is trying to demagnetize the material. That is always pointing in the opposite direction of the magnetization. If this field is always present, then every time we make a measurement, we design an apparatus, so we have to remember this, that the field which is acting on the magnetic materials is not only the field that we can apply externally, but is always the sum of the so-called applied or external field and the demagnetizing field, which is as always the action of pointing in the opposite direction to the magnetization. Oh, but this is very complicated because then it will mean that even if I magnetize, if I eliminate the stray fields because the magnetization is uniform inside the material, we have no guarantee that the magnetizing field is uniform. The magnetizing field will be a solution of this problem. So exactly like the electric field is uniform inside the capacitor only as a limit. So the magnetizing field will depend on space and also on the specific shape that we choose. Then everything will be extremely complicated, apart some very interesting cases that comes from the mathematical treatment, essentially, of the equation. So the question is, suppose that I have a body, a sample, or at least a material, where I can generate a uniform magnetization. My question is there any special shape for which I can also have a uniform demagnetizing field? Because if it's not uniform, it means that I have to take a computer and make a solution. Is there any simple case where this uniformity is generated by the shape itself? And the answer is yes. And the set of shapes that generate the magnetizing field uniform inside the material are the ellipsoids of revolution. So there is including the sphere. So if I limit to these shapes, so ellipsoid of revolutions, I assume uniform magnetization, then if I compute the magnetic field, I find a solution that I can demonstrate it is uniform inside the magnetic body. If it is uniform, as also the magnetization is uniform, the relation between the demagnetizing field and the magnetization is a number, or better, a tensor, because it will depend the direction where the magnetization is. This number n is called the demagnetizing coefficient, corresponding to a certain ellipsoid. The magnetizing coefficients are something extremely important in magnetism. So, how to start from here? Let's say that these demagnetizing coefficients have the following properties. That if I take three directions, so the three main axes, the sum of the three main demagnetizing coefficients must be 1. The typical cases are those illustrated here. Take ellipsoid of revolution, and so imagine to take a sphere and then to deform in two ways. So from in one direction, I take the sphere and make it long, so like a cigar, and this is called a prolate ellipsoid, or I can make it flat, and this ellipsoid is called oblate. Then, once I've broken the symmetry of the sphere in this way, then there is another symmetry to break, is to choose the magnetization direction. So I can either choose to magnetize the body, let's say, parallel to the direction I've deformed, or even perpendicular. So in the picture here, you find what happened if you apply the magnetization in the same axis of your deformation. So for the prolate, what happens? That you have something, an ellipsoid, which is long. So imagine like compass needle. And the magnetization is constrained to be in the same direction. Constraint, it means we artificially set like this. What will be the magnetizing coefficient? You can compute and you find formulas for this, analytical formulas, if it's in the case of ellipsoid. The more prolate it is, and the more the magnetizing coefficient will tend to 0. Take the opposite condition. So take the oblate, magnetize along the symmetry axis. So you're taking something which looks like a disk, and you're trying to magnetize in the perpendicular direction to the disk. It already looks something not so good, no, not so how to say. Is not in a direction of easy magnetization, but if you force it, you will find a strong demagnetizing field, a strong action of the magnetization. So if you take this curve here and go towards 0, you will find that the magnetizing factor tends to 1. So what are the cases in which this demagnetizing action is negligible? If I take something which is very long, so for example, something which is infinitely prolate, or for example, an infinite rod, or a toroidal sample, or whatever, if I try to magnetize something in the direction perpendicular, so instead, if I take a plane and I try to magnetize in direction perpendicular, the magnetizing force, the magnetizing field will be the maximum possible. Then this has a lot of consequences, not only on the way we use magnetic materials, but also on the way we measure magnetic material, especially if we want to measure the intrinsic property, not the property of the object, but the property of the material. So what I have to do if I want to measure a material that I don't know, they have created in the lab and they want to observe the property. I need to produce some shape where the demagnetizing effect is minimized, or otherwise I have to take into account. For example, if I produce a sphere, it would be a good compromise in the sense that analytically, I know that the magnetizing coefficients is equal in the in all the directions, and so it's equal to 1/3. Not in any case this is useful or it's practical. This demagnetizing field is proportional to the saturation magnetization in ferromagnet, so it can be extremely high, extremely large in soft magnetic material. And in any case, it's never negligible. So what do we have next? So what are the shapes? If, for example, in measurement, in typical measuring situation, what are the shapes that are commonly used where I can neglect or put 0 the magnetizing effect? The first is toroids. So a typical situation where the magnetizing field is low or negligible is a material which is closing with itself. It's clear that then I have to generate the field by windings wires around it. But this is one of the cases, and this is very much used for the characterization of soft magnetic material, where I have a negligible demagnetizing field. If I cannot do things like that, at least I can produce a very long rod and magnetize along the rod. If I have no way to make a rod and I have to limit to something which is flat, and then it's better to choose a magnetization direction in the plane and not perpendicular to the plane. Or otherwise, I will have to deal with enormous demagnetizing fields. If the shapes are non-ellipsoidal, then we go a lot into trouble. So In the previous slide, I've not commented upon that, but it's still possible for rectangular shapes to have approximate the magnetizing coefficients. So you have tables and calculation for these magnetizing coefficients depending on the aspect ratios. But if we want to look, if you look for an exact solution, then you will have to consider the fact that the magnetizing field is not uniform throughout the sample. And this may create a lot of problems. For example, if you want to characterize the material. Okay, with this, we can stop here with the magnetostatics. If there are questions up to now, you can also ask it now, or otherwise at the end. Because otherwise, we can proceed and describe a little bit, say a few words about the units and the international system. So I think we can stay within 1 hour. If not, I can go. Okay, so units in magnetism. So this is a really crucial issue. And the reason is the following. For Maxwell equations, not only we have different units between the international system and the CGS, but the problem is that we have different equations, and this creates a big confusion. So while we write that the divergence of the electric field is equal to the charge density divided by epsilon 0 in the CGS, we put 4 pi times the charge density. Then in the CGS, you also changed the fourth, and you use explicitly the speed of light. What is the beauty of the CGS is that if you look at the equation, there is only one constant, that is c, the speed of light, and nothing else. So in a certain sense, from the point of view of electromagnetism, the CGS is more obvious. I mean, why do we need two constants, mu 0 and epsilon 0, while the only clear parameter in the electromagnetism is the speed of light? Why? In fact, the CGS eliminate and just put C. What is the price to pay? The price to pay is that, for example, the relation between the magnetic induction and the field is no more just a sum, but you have to put a 4 pi in front of m. So magnetization is not magnetization, it's 4 pi m. What are the units? Well, let's read what it's written there. The quantity B, the magnetic induction, in the international system is unit in Weber, so the flux per meter square, or Tesla. This unit is quite large in the sense that the magnetic field generated by the Earth in our planet, the surface is some micro Tesla, so something which is very small in this unit. In the Gaussian unit, the B field is measured in unit Gauss. The conversion factor, as you see, is 10 to the minus 4. The field H in international system is measured in amps over meter. Amps over meter, again, for the Earth field is equal to 25 amps over meter. So it's a small unit, a unit that works well with small magnetic field. In the Gaussian unit, they use the Ørsted. In the Gaussian unit, the Ørsted and the Gauss are the same thing. This seems strange, but it's exactly like this. So they use two different names of the units for the same thing, essentially. In fact, you see that B is equal to H in the QGIS. Practical conversion is written here. So 1 Ørsted is more or less 80 amps over meter. So it's a unit which is intermediate, not too large, not too big. In the international system, you measure the magnetization in the same unit as the field, so amps over meter. In the TGS, you use mu over cubic centimeter. Mu0 m in the international system, you can measure in Tesla. This is very often used because saturation of most of the ferromagnets is in the range of the Teslas. So 1.6 Tesla, 2.2 Tesla are common values. So it's something to remember. It's quite easy to use not m, that will be 10 to the 6 amps over meter, but you use the unit Tesla. So mu0 times m is very often used. Sometimes for magnetic materials, the product mu0 m is called I, sometimes J, so-called magnetic polarization. So as the names, as far as I know, magnetization means measured in amps over meter. Mu0 m is measured in Tesla, and you still call it magnetization. But if you say polarization, magnetic polarization, you generally mean that you directly refer to mu0 m. This is just to remember, because then in books, in papers, in whatever, you find everything. What else? In the Gaussian unit, 4 pi m is measured in Gauss. My personal comment is that the presence of 4 pi m in the magnetization create, while for electromagnetics, I can agree that the GGS is beautiful. If in terms of magnetic materials, is just confusion, enormous confusion. So something that I've never get used to. So I for example, myself, I'm used to the international system, and the other units for me are really strange and unusual. Okay, so we have to stick to international system in any case, but in books and in publication, especially the research done by American groups, you find the GGS. So you can, always useful to be able and to know and to convert one unit into the other. This is always, unfortunately, important. But up to now, this is old international system. What was 3 years ago, not what do we have now. What changed in this international system 3 years ago? They fixed a lot of physical constants. So before 20 May 2019, only the speed of light was fixed. Maybe something else that I'm forgetting. But now we have fixed the value of the Planck constant, the value of the electronic transition of cesium. Maybe this one is the one that was already fixed. The elementary charge, the Boltzmann constant, the Avogadro constant, and the units that are used for the candela definition. What's the problem for us? That's as scientists has agreed to fix elementary charge, then unfortunately we cannot keep in the Maxwell equation as they were before. Why? Because there are relations that are involving mu0 and epsilon 0 and the elementary charge, so that we cannot arbitrarily fix mu0 anymore. This creates a lot of things. First of all, in the all the international system, in the end, we could use mu0 as a fixed numerical constant. That is 4 pi times the minus 7. The use of international system and the CGS was just a matter of individual preference. You could, in any case, pass from SI to CGS because it was in the CGS, as I told before, in a certain sense, it was more clear. The only true physical constant that was there is the speed of light, and that's it. And you don't need nothing more. So that was why physicists liked it more than the international system, and was very much used. For example, if you take book of physics that are at least 3 or so years old, because you don't need to fix mu0 to a numerical constant in the old systems. But now, in the new international system, we cannot fix one of the two. So, as we know, the product of mu0 and epsilon 0 is related to the speed of light. So we have only the freedom to fix one in the old international system. But this, having fixed the elementary charge, this freedom we don't have anymore. We don't have anymore. So we have to measure or mu0 or epsilon 0. What does it mean? It means that in the CGS, where we had only one constant, the speed of light, this system is not compatible with the physics anymore. It became obsolete. So it's a way to describe electromagnetism that is not compatible with anything anymore. So it must be abandoned, also by the Americans, by the way, because you cannot pass any more from one to the other, because now there is freedom in mu0. Mu0 has to be fixed by some measurement, has to be determined in some way. And in the CGS, there is no way to do it. So the way how CGS equations are written, it makes no sense anymore. So the new Maxwell equation contain one parameter, which is mu0, that need to be measured, cannot be fixed arbitrarily to a numerical constant. So meteorologists have considered this fact very carefully, I would say, and they have fixed this value as the one written there. But the big question is, where does it come from? Who did the measurement of mu0? That we working in electromagnetism, as we have always considered as a numerical constant. This is quite beyond what we do here. The point is that there are relations involving mu0, the Planck constant, the speed of light, the elementary charge, and, for example, something else. For example, the fine structure constant. This fine structure constant, I wrote here, it's almost equal to 1, but it's almost equal just to give a certain typical number, no? It's a very important constant that appears in atomic physics, high-energy physics, quantum electrodynamics, cosmology, but not directly in electromagnetism. But as this equation is valid, and as physicists working in high-energy physics are able to measure the fine structure constant with very high accuracy, then it turns out then mu0 can be fixed by relating it to the fine structure constant. And this is where this expression comes from. So the change in numerical value with respect to 4 pi 10 to the minus 7, as you see, it's 10 to the minus 10, so very small. And in practice, you can continue safely to use the value of 4 pi 10 to the minus 7. But it's the principle which is important. And I would also like to add that the principle is very important, because Maxwell equations themselves, they are not anymore self-standing theory, unfortunately for Maxwell. Now they need a certain coupling that is given by other more deep and profound and with a more deep physical meaning with respect to electromagnetism. And these are quantum theory of essentially quantum electrodynamics. So not only we had to introduce a numerical and measurable value for mu0, but the equation of electromagnetism, instead of being a fundamental theory of the physics, has changed role. Now is just a model. So an approximate model where quantum electrodynamics goes macroscopic. And this, in a certain sense, is something that could lead us to some thought in general. Oh, there is a question. The fine structure constant is the true universal physical constant of electromagnetism because it is dimensionless and therefore not related to the choice of physical units. If you like, but Stefano, that's also, this is also my personal point of view, not shared by anyone, not shared by everyone. But the point is that now you cannot have electromagnetism Maxwell equation alone, in a certain sense, as you had before. So you have to derive the equation of electromagnetism from something that you consider more physically deep. So, as far as I know, there has been discussion concerning the fixing of the elementary charge or not. This was discussed, but then I mean, there were very strong positions in favor because of the Josephson effect, and we cannot fix both the elementary charge and the magnetic permeability. Exactly. In fact, that's not the point. Because they are related by the fine structure constant that has an experimental value that cannot be calculated theoretically, so it cannot be fixed in advance. That's the point. Yes, exactly. No, I meant that at the beginning, they could also choose to fix alpha and not to fix E, so the elementary charge. But then probably it would mean that all the quantum electric measurement would lose some beauty, and that is not acceptable at the moment. So in the end, this is probably a good compromise. Even if you think about it, if mu0 is measurable, so it's not fixed, then also our meaning of B field and H field is quite unclear, because they are not just the same thing, no, in vacuum. Okay, but if you like, there is this paper here by Goldfarb. Maybe I also mentioned this the other time, where it's well discussed, this issue. Very interesting, if you like. So references. So I've taken this from the book of Jackson, Classical Electrodynamics, from the book of Bertotti, very nice, for magnetostatics and so on. I've taken a few things of the magnetizing field by the book of Fausto Fiorillo, Characterization and Measurement of Magnetic Materials. Very, very good source for measurement techniques in general. And I mention again this publication by Goldfarb. Okay, I also put at the end, if there is someone that would like to make exercise as an exam, that we also can accept. If you like to make practical exercise in magnetism, there is a list here. So if you're interested, you can just contact us. And with this, I think I can stop. And if you have questions, please, you can ask.
Resume recording. Okay. So in the last lectures, we said that, as I told you, Maxwell equations describe very well almost all applications that we have. But the Maxwell equations do not tell us anything about the origin of magnetism. Why is it like that? Because in order to apply Maxwell equations, we need the constitutive relations. Constitutive relations tell us how it behaves if we bring it into a magnetic field or in an electric field. And this depends, of course, on the properties of the material, like the susceptibility or the permeability. So one way, of course, to access to this susceptibility or permeability, even without knowing anything about the origin of magnetism, is to measure the relation between magnetization and magnetic field. And this we can do very easily, let's say, and this was done already 200 years ago, almost by Faraday in 1845. And he invented this kind of experiment where we have a magnetic field. So you can see here South Pole and North Pole, and we suspend our magnetic material that we want to investigate in between on a wire, and then we let it freely rotate. And what he found is that there are two different kinds of material. One material that he called diamagnets, and they rotate 90 degrees with respect to this magnetic field, and magnets which rotate along the direction of the magnetic field. And nowadays we know, of course, that this is related to the fact that diamagnets already, as I mentioned it last time, have a negative susceptibility, so they are repulsed by a gradient of a magnetic field, and magnets instead, which are nowadays called paramagnets or ferromagnets, are attracted by the gradient of a magnetic field. And this is exactly the experiment that still we use, the experiment, another experiment of Faraday, the Faraday balance. You can see here a picture of such an experiment of the Faraday balance, and it's based here on the Faraday force. This equation here describes the Faraday force, so the force on a magnetic material in a gradient field, magnetic field. And you can see here to derive this, calculate this expression here is not that easy. It's simpler if M is independent of B, and especially if we consider only, let's say, a gradient in the Z direction and B in the X direction and M only in the Z direction, then it's easier to calculate. And written in this way, of course, we can easily interpret this expression, this equation here. And you can see that M will feel a force either towards higher fields, or it will be repulsed from the higher fields, so outwards if it's a diamagnet. Okay. Nowadays that all materials are magnetic, but we have different kind of magnetism. We have diamagnetic materials, as already Faraday discovered, paramagnetic materials, and ferromagnetic materials. And you can see here in this periodic table that from the element point of view at room temperature, we only have iron, cobalt, and nickel, which are ferromagnetic. And here in this magnetic periodic table, also gadolinium is considered ferromagnetic, because gadolinium has a transition from ferromagnetic to paramagnetic exactly around room temperature. And then, of course, there are some rare earth elements which have this transition at lower temperatures, so they also become ferromagnetic. Along the, let's say, ferromagnetic materials, there are also antiferromagnetic materials, this green here, like manganese or chromium. Of course, these are very, very close to ferromagnetic materials, and this we will see in the coming lectures. Okay, now we want to study from where is coming this magnetism. And the first hint was given by Ørsted in 1820, and already I mentioned also this in the introduction of our lectures. So what considered Ørsted? It was known at that time that when a ship got struck by a lightning, then very often they could not orient anymore. So they got lost somewhere in the sea, and it took some time to get back on the route they were pursuing. So it was understood that the compass somehow was disturbed by the lightning. And since the lightning, it was known already, was related to electricity, Ørsted thought, of course, there must be a connection between an electric field and a magnetic field. So if I bring a compass close to an electric field, so you can see here this electric field, which is indicated by a voltage source, let's say, then the compass somehow should move. Fortunately, the legend says that Ørsted had a student that did not obey the instructions of Ørsted, and he made a mistake, and he connected the two poles of our voltage source, and in this way, with a wire, and in this way, an electric current was flowing. Because this was a fortune, because while Ørsted did not observe anything with the electric field, with the electric current flowing instead, the compass moves. And this is also a very nice experiment you can do. It's very simple to see that. And so it was clear that there must be a connection between an electric current and the magnetic field. And it was understood then later, and you already know this now after the lectures of Vittoria, that the Maxwell-EMPIR law describes that electric current produces a magnetic field. So you can see here this current is surrounded by our magnetic field. On the other hand, this idea immediately inspired Ampere. In the same year, he did his theory on, let's say, small ring currents, which create a magnetic moment, and the sum of all these magnetic moments will give the magnetization of a magnetic material. So the magnetic moment is given simply by our electric current times the area of this ring here, of this, where it is flowing, this ring current. In this way, we can get a magnetization, but one of the problems that was considered by Weber, for example, was what's happening to Joule heat, because it was already known that, of course, an electric current heats up the material, heats up the wire where it's flowing, and because, of course, there's some power dissipated by the resistance in the wire. And why we don't have this in a magnetic material if we have really true ring currents flowing? And Weber, for example, he suggested that these ring currents might be very, very small, microscopic currents that are flowing, and they are not sufficient to heat up the material. But of course, it was not really a very satisfying explanation, let's say. So these microscopic currents then were, for example, considered to be could be an electron which is moving around a proton, for example, and this creates a magnetic moment. But of course, at the time of Ampere and Ørsted, neither the electron nor the proton were known already. So the electron was studied in the second half of the 19th century. So exactly at the time, nobody had an idea. Instead, this idea of the electron moving around the proton, or a nucleus, let's say, came out with the Bohr atom model. And in the Bohr atom model, first one speaks about an elementary magnetic moment, so the magnetic moment of one electron. So it's clear that somehow a magnetic moment is related to an electron orbiting, so to an angular momentum in some way. And this relation already was known because it was also known that a copper rod that is spinning is easily influenced by a magnetic field. And this relation, the slides are very slowly changing, unfortunately, today. And this relation can be described in this way. So the magnetic moment is proportional to an orbital momentum. Again. Okay. In 1915, Einstein and de Haas, in fact, they wanted to give a proof of the existence of this EMPIR molecular currents by doing the following experiment. And you can see here a coil which is producing a magnetic field and a ferromagnetic rod. They used iron on a torsion fiber, suspended on a torsion fiber. And so you will see a rotation when you have a magnetic field. And you can measure this. So you can measure the proportionality between magnetization of this magnetic material and the angular momentum that you observe. And in this way, you can determine, of course, this proportionality constant gamma. And this was really observed, and there was a very nice proof. But unfortunately, it was not yet understood at that time that in iron, the magnetization is not caused mainly by the orbital momentum of the electrons, but by the spin momentum. But however, of course, the experiment itself is very valid. So how can we calculate gamma? Simply starting from this idea that we have an electron that is moving around the nucleus, positive nucleus, which could be a proton or something else, with a certain mass and a certain velocity at a certain radius. We can calculate the magnetic moment by considering I times A, knowing, of course, that L is equal to R cross P, the momentum. And in this way, I leave this to you at home to do that, because I think it's very elementary. You find that this proportionality constant is E, the charge of the electron, divided by 2 times the electron mass. And this proportionality constant is called the gyromagnetic ratio. Please consider that E is negative. So we have a negative charge, of course, in this calculation. And so M and L point in opposite directions. Sometimes you will find written gamma in this way. Sometimes you will find here a minus sign in front. But please, if you find a minus sign, then consider that this elementary charge is considered to be positive. Of course, this brings us back to our elementary magnetic moment, which is called the Bohr magneton, and which is the magnetic moment of an electron in the Bohr atom model. And of course, already considering the quantization of the Bohr atom model so that the electron cannot take infinite states and is confined to quantistic states. And in this case, we have also here H bar, the Planck constant, because L becomes, of course, an operator in quantum operator. But let's not move too much into quantum physics, because in this lecture, we will still stay on classical theories. This is just to make a connection. Okay, now let's see a little bit what happens to our magnetic moment when we bring it in a magnetic field, because of course this we wanted to describe. We wanted to know what happens to our magnetic material when we bring it in a magnetic field. So let's consider that we have this elementary ring currents of ampere, an electron moving here in the XZ plane. We have a magnetic moment produced by this ring current. And of course, this magnetic moment is proportional to L, our orbital momentum or angular momentum. Now, let's consider that we bring it in a magnetic field. So we have a magnetic field in the Z direction. Consider that an electron in a magnetic field will feel a force. And this, of course, you should know already, will feel the Lorentz force. And the Lorentz force tells us that this electron moving in the X direction in a field in the Z direction will feel a force in the Y direction. If we have a force, then we always have a torque. The torque, of course, is proportional to R cross the force. If we have a force, then we will have a change of angular momentum. So the torque is in the minus X direction, since it's R cross the force. And in this way, we will have a change of the angular momentum also in the minus X direction. But now knowing that gamma is negative, our gyromagnetic ratio is negative, then we will have also a change of magnetic moment, but in the plus X direction. Let's plot this here. I hope you can see this well. So we have this delta L, change of angular momentum, and we have a delta M as a consequence. So delta M will change if we bring it in a field. And you can see here that the vector M will be rotated at an angle theta with respect to the first position here. So what does it mean? This means that we have a precession motion. So our magnetic moment will precess around the magnetic field that we have here. This is very important to remember. So this is the dynamic behavior of a magnetic moment in a magnetic field. With which frequency will it process, especially if we think about our electrons, so think about an elementary magnetic moment, mu Bohr, then the magnetic moment will process at a frequency which is proportional to the magnetic field. And this is the so-called Lammer frequency. So the magnetic, the faster it will rotate, precess. So the magnetization dynamics, therefore, is described by the torque equation. So we have that the change of magnetic moment in time is proportional to M cross B. Of course, now maybe you should one moment be astonished and say, okay, but isn't it that if I have a magnetic field and I bring a magnetic moment in this magnetic field, that this magnetic moment will align to this magnetic field? This is something that we observe, of course. I mean, take a compass. You have a magnetic, let's say, a magnetic material which represents our magnetic moment. You bring it in a magnetic field and it will align in the direction of the field lines. It's exactly what we saw in the experiment that we had at the beginning. No? So this is somehow, let's say, strange. No? We do not expect that our compass will start to rotate around the direction of the magnetic field. No? But of course, this is the dynamic equation that we see. But what we did not consider in this dynamic equation is that we have a damping. So usually our magnetic moment will precess around this field direction, but due to the damping, which is somehow a connection between the magnetic system and the atomic system, so the crystal system, let's say, a transfer of energy will happen from the magnetic system to the crystal, and the magnetic moment will lose energy and will spiral down in the direction of the B field. And this happens very, very quickly. So you can see here that tau is about 0.1 nanoseconds. And the oscillation frequencies that we have in ferromagnetic materials are in the gigahertz range. However, we can compensate this damping if we switch on a magnetic AC field at the right frequencies. And in this way, we can compensate the damping and we make the magnetic moment or magnetization stably precise around the B field. And this is called the ferromagnetic resonance, because only at the resonance frequencies we can compensate the damping. And this resonance of the magnetization we can measure, of course, because we may measure a signal that is produced at the gigahertz range coming from our magnetic material. So this was about the relation, let's say, between angular momentum and magnetic moment. I would like to show you maybe another quick experiment. This is something that I will not explain to you, that maybe you should think about, because it's a nice experiment, but it's a little bit difficult to understand. It is somehow related to this, let's say, angular momentum and torque and electric current, let's say, but it's not exactly what I showed you here. But you can think about this at home. I will share my screen and give a look to this experiment here. So you can see here a screw, and you can see a small permanent magnet. The screw, of course, is iron, something steel material. Then you can see a battery and a wire. And now we let the current flow through this screw. And you can see that this screw rotates. And so in the next lecture, I will ask you, how is it working, this experiment? Okay, let's move on, because of course we want to know now that we know, okay, one origin could be these ring currents in our magnetic material. Now we want to know, why do we have different kind of materials, magnetic materials, let's say. This is still something that we did not understand yet, that we did not discuss. Last time I already showed you this picture here, and we said the diamagnetic material have a negative susceptibility and that M is proportional to H. So chi is a constant, let's say, and it's also constant in temperature. However, chi is relatively weak, very small. Let's try to understand something about this. And of course, if you think about a magnetization that is pointing in the opposite direction of the field, of the applied magnetic field outside, then if you studied electromagnetism, then you think immediately about the Lenz law. So what does the Lenz law say? It says that in a time varying magnetic field, a moving charge reacts in some way so that it will produce a magnetic field that opposes the initial field change. So if we have a field change, then our charge here will start to move. So we will get an electric current, which will produce a magnetic moment or a magnetic field, let's say, that opposes this field change. This is, of course, something that reminds us eddy currents, no, in a conductive material. And something very similar seems to happen here in diamagnets, but it has nothing to do with eddy currents, let's say, because diamagnetism may also be a property of materials which are not conductive. But of course, it's very nice idea to understand diamagnetism. And in fact, Feynman did this classical interpretation of diamagnetism. And we can derive in this way the diamagnetic Chi susceptibility. So let's start from the law of induction. So if we have a field change, then we will, of course, have an electric field. So by using the Stokes law, we can transform this rotor field in a line integral, and we can the proportionality between electric field and our magnetic field change. So this is the induced electric field, induced, of course, by the magnetic field change. If we have the electric field, we will also have a force, the Lorentz force now in an electric field, and then we have a torque on the charge. So let's see. If we have the torque, then we know that we have a change of an angular momentum. And this is proportional again to a change of a magnetic field with the proportionality constant, the charomagnetic ratio. So we can get the proportionality between the changing magnetic field and the changing magnetic moment and the changing magnetic field. And in this way, of course, we can write M proportional to B, and we get the diamagnetic susceptibility. You can see here we have the electron charge, we have the electron mass, and we have the radius of the assumed, let's say, orbit of our electron. And chi is negative. Also this we get already. So the stronger is B, the stronger is M. So we can consider, of course, that diamagnetism is kind of induced magnetism, while paramagnetism is not at all like that. But before going to paramagnetism, I want to show you maybe a diamagnetic material. It's not so often that you can see that the diamagnet is really repulsed, so that chi is negative, by a magnetic field. And I'll show you again a small experiment here. Let's share the screen. Okay, here you can see a pyrolytic carbon on several permanent magnets, very strong permanent magnets, and you can see that it fluctuates on top of this magnetic field, so it's repulsed. So if you move slightly, you can see here this pyrolytic carbon plate, and from below you can see here it's levitating. So this is magnetic levitation with the diamagnetic material. So this experiment is not so easy to do with other diamagnets like copper or something like that, because these materials usually are too heavy to show you this effect. But with a very light material like pyrolytic carbon, you can show this levitation of a diamagnetic material, and this is nice. But now let's move on to paramagnetism. Paramagnetism is very different from diamagnetism, we said, because already in the first lecture I mentioned it, because we have pre-existing magnetic moments, as you can see here below. So diamagnetism is induced and paramagnetism has these magnetic moments. Now, we don't know anything about from where coming these magnetic moments. Now, let's say they could be this orbital motion of the electron, an elementary Bohr magneton, for example, or could be a spin moment, or it could be the ring currents of EMPIR. Does not matter. However, Langevin did a theory on paramagnetism in 1905. And he tried to describe the behavior of a paramagnetic material in a magnetic field, considering two different energies, let's say, two different effects. One effect is if you bring a magnetic moment in a magnetic field, then the magnetic moment will align with the magnetic field. So all pre-existing magnetic moments, if they are already in the material, they will align with the magnetic field. And this is Zeeman energy, because Zeeman energy is lowest if all the magnetic moment is aligned. On the other hand, we have to consider the thermal energy. So all magnetic moments somehow will be moved, shaken by the temperature. And in this way, if the temperature is high enough, we will get a zero magnetization, because overall magnetization of magnetic moments pointing in all kinds of directions will be zero. So at high temperatures, we should not have any magnetization. The thermal energy, of course, is given by the Boltzmann energy, where you have the Boltzmann constant times the temperature. So at a certain point, of course, at a certain field and a certain temperature, you will have an intermediate state. So the magnetic moments will be aligned, but maybe not completely aligned with the magnetic field. So you have to do an energy balance. And this energy balance we can do if we consider Boltzmann statistics. So our Zeeman energy in this way with a certain angle between the magnetic moment and the magnetic field. And the Boltzmann factor describes the probability to find a magnetic moment in this certain direction at a certain temperature T. So now doing some Boltzmann statistics, we can get the average value of the magnetic moment, again at a certain temperature and a certain magnetic field. Now calculating this, it's not so difficult to do. I give you here some hints how you can solve this equation here, and you can do this if you're interested. And you will find that the average magnetic moment is the single magnetic moment times the so-called Langevin function. So this function has the name of Langevin. How does this Langevin function behave? Let's plot it here. It saturates at a value of 1. So if the argument is 1, then it saturates. And at the beginning, so for small arguments S, it's quite linear, let's say it's almost linear. And it is 0 at 0. So it starts at 0. So with this Langevin function, now we can interpret the result that we got from our energy balance. So we have a magnetic moment is the average, the magnetization is the average magnetic moment times the number of moments per volume unit. And having in mind, of course, that the average was proportional to the Langevin function, then we can interpret the result, see that if the argument of the Langevin function goes to infinite, then we will get something like saturation, let's say, magnetization saturation. And because we get to the maximum value. And the argument gets infinite. Of course, you can see this here easily. If the field is very, very high or the temperature is very, very low. So at very low temperatures, all magnetic moments should be aligned. At at least if we apply a very, very small magnetic field. Of course, at an extremely high magnetic field, all magnetic moments in the paramagnet will be aligned. So you're also at saturation. If S goes instead, then this means that the temperature is infinite or the magnetic field is zero. And in this case, of course, our magnetization is zero. So if we do not apply a magnetic field, then we do not have a magnetization, and this is paramagnetism. So this is clear behavior of paramagnetism, and already I described this the last time. So we see here these pre-existing magnetic moments at high temperatures. We have a kind of linear behavior because the magnetic moments try to align against the temperature. At lower temperatures, of course, they will align more easily, and we can even reach saturation. Let's check a little bit what happens at high temperatures. So if temperature is very high, we say we have this linear behavior, but can we also say something about chi, the susceptibility, and we can expand our Langevin function in a Taylor expansion, and we get this function here 1 over s plus s divided by 3. And having in mind always s is m times p divided by kpt, then we can calculate this formula, and we find immediately that m is proportional to h divided by t. So the susceptibility, this is the susceptibility here, is proportional to 1 over t. And this, of course, is the Curie constant here, C, this proportionality constant. We know that 1 over chi is linear in T. So this is the famous Curie law. Before moving on to ferromagnetism, I would like to show you the experiment of Faraday. So the Faraday balance, let's say the fact that also a paramagnetic material is attracted by a field gradient. Usually this is something that is very difficult to see because paramagnetic materials are too heavy to be easily attracted by a field gradient. You will need very strong field gradients, of course, but in very certain cases, you can, however, do that. And I show you here a short movie of the lecture of Professor Lewin. He was a lecturer at MIT. He was a lecturer at MIT a long time ago. And I recommend, if you're interested in physics in general, these were lectures for undergraduate students. So at a very basic level, but very, very nice because he did a lot of experiments. And I will try now to share this video with you. Hope it will work. Okay, I have to go back just a bit. And I have to switch on. Okay, I hope you saw this external video. That somebody told me that he could not see anything, but it's strange because I tried this before and it worked perfectly. But if you did not see anything, then please just go to the material that I shared with you, and you can see this movie. It's on YouTube, and you can check it out yourself. Okay, so this was just a video to show you, of course, magnetic oxygen, quite strange now, sounds strange. But in certain cases, of course, you can apply also this experiment of Faraday to paramagnetic materials. But now there's still something missing, and it's ferromagnetism, and we still have to do, let's say, a classical theory of ferromagnetism, and we have to understand what is the difference between paramagnetism and ferromagnetism. So ferromagnetism, I told you, of course, or this was also mentioned in the video here, is much, much stronger than paramagnetism. And so the susceptibility is much higher. And that's the reason why it's attracted, a ferromagnetic material, by a field gradient. And you can see easily the force. So the difference is that, again, we have pre-existing magnetic moments, and this is exactly the same as we have in paramagnetism, but ferromagnetism is a cooperative phenomenon. And exactly for this reason, it's much stronger than in paramagnetism, because in paramagnetism, each magnetic moment aligns individually with the magnetic field, while in ferromagnetism, a single magnetic moment aligns spontaneously with all his neighbors. And this is a very, this is the feature, let's say, of magnetism. So M as a function of H is very similar to paramagnets, as we can see here, but it's much stronger. So you can see here that at high temperatures, for example, we have again this linear behavior, while at lower temperature saturates the magnetization. Again, we have this behavior that 1 over chi is proportional to T, the temperature, but only a certain temperature, a critical, so-called critical temperature. So even a ferromagnet will behave like a paramagnet, but above a certain critical temperature, and we will calculate this critical temperature now. And below this critical temperature, M is a function of T and has a typical shape, as you can see here. And M becomes maximum at T equal to 0. So it reaches MS only at a 0 temperature. Just one remark, one thing that you cannot see very easily in this slide here is that we have hysteresis. So at 0 magnetic field, magnetization is not 0. It aligns spontaneously. We have a certain magnetization. This is very different with respect to paramagnets. And we have hysteresis, so coming from positive fields or coming from negative fields will not give the same magnetization value. We will have a positive value and a negative value. And this value, I mentioned this last time, is called the remanence. So the remanence is not the same if you're coming from different magnetic fields, from positive or negative. So we have hysteresis. So Weiss, after the theory of Langevin, tried to apply the Langevin theory to ferromagnetic materials. And he had this very great idea of the fact that a single magnetic moment, which exists in a ferromagnetic material as it exists in a paramagnet, will align with all the neighboring magnetic moments that are surrounding it. So all the neighboring magnetic moments create somehow a magnetic field that this single magnetic moment feels, of course. And this is a very reasonable assumption, and this field is called the molecular field. And this molecular field was considered by Weiss to be proportional to the magnetization, as of course it should be. So applying Langevin theory now to a ferromagnet means that in the argument of the Langevin function, we have not only the magnetic field that is applied from outside, but of course we have also the magnetization. So this Weiss molecular field, we have a field that is proportional to the magnetization. So at this point, this equation here, unfortunately, becomes a transcendental equation, and we only can solve this equation graphically. And this I will show you in the next slide. So give a look to this next slide. Here again, we write the argument of our Langevin function as x, and m becomes a function of x. And in this way, we can write two functions. Function 1, m1, is proportional to the Langevin function as a function of x. And function 2 instead is, if you express m from this equation here as a function of x, then you will have this m2. And of course, we will find the solution of this equation here when we have a crossing between these two functions. So for any x where we have so m1 is equal to m2, and this we have to solve graphically. So now let's plot m2 here and m1, of course, which has the shape of the Langevin function that we saw before, going up to ms as a function of x. Now you can see that m2 will change slope, and the higher is the temperature, the higher is the slope of the function m2. And we will have certain crossings with the function m1. And these crossings depend on the temperature. They are temperature dependent. You can also see that at a certain temperature here, T3, we have a crossing only at 0, and T3 we can call the critical temperature, because above this critical temperature we will not find anymore any crossing which is not equal to 0. So we don't have a solution not equal to 0 of this equation. So this means that ferromagnetic behavior exists up to this critical temperature Tc, where we have a solution of this equation, and above it, it does not exist. Of course, what I did not mention at the beginning is that in this calculation, we did not consider the applied magnetic field, because the applied magnetic field, as you can see here, would shift this function m2 parallel to the to these lines here, which are crossing at m equal to 0. So already you can see also an interesting remark is, if we have an applied magnetic field from outside, then you will always have a crossing. However, usually we don't have a crossing above the critical temperature, and this critical temperature, I already tell you now, is called the Curie temperature. Above this behavior, above this critical temperature, we have a paramagnetic behavior and a paramagnetic phase. Below, we have a ferromagnetic phase. And this happens in all ferromagnetic materials. Now, let's understand a little bit more about this Curie temperature. So if we consider that we are in the paramagnetic phase, then we know that we have a paramagnetic susceptibility, and we have this proportionality that chi, the susceptibility, is proportional to 1 over T. only in the paramagnetic phase now. Now, having only H, we have again the Weiss molecular field, and we can calculate this equation, and we will find that now the susceptibility of a ferromagnet in the paramagnetic phase is equal to C divided by T minus C times lambda, and C times lambda is exactly this critical temperature. So the Curie temperature. So the Curie temperature is proportional to the molecular field constant lambda and C, the Curie constant. So one thing that was really puzzling everybody at the time was that lambda, if you calculate it, in order to describe the typical magnetization that we have in a material, had to be extremely high. So if you calculate it for a typical ferromagnetic material, you will get that the Weiss molecular field should be inside the material, should be about 1000 Tesla. So 1000 Tesla, if you're not that familiar with the numbers of magnetic fields, is an extremely high field. We can produce this kind of fields in a lab, but only with destructive methods where you have to implode a coil and you get these high fields only for fractions of seconds. So these are really very, very extreme fields. We also understand that they are extreme because they have nothing to do with the magnetization. So if we consider the fields, let's say coming from a ferromagnet, if you calculate the magnetization in Tesla of iron, for example, you will find that iron has a magnetization of about 2.2 Tesla. So 2.2 Tesla of magnetization, it's very strange that somehow there should exist a Weiss molecular field of 1000 Tesla. And this had to be understood, so it was clear, of course, that this theory of Weiss is a very beautiful phenomenological theory that describes very well the behavior of ferromagnetic materials. But it's a phenomenological theory. It does not tell you anything about the origin of ferromagnetism. And this brings us to the end of this lecture, because the origin of ferromagnetism we will study in my next lectures on Monday morning. And there we will try really to understand from where is coming exactly the magnetic moment and magnetization of a material. So here's the summary, and here you can see a few questions, and you should be able after this lecture to answer to these questions. And next time I will torture you a little bit at the beginning of the next lecture and ask you these questions, and I hope you will be able to answer so that we will see if you were awake during this lecture or not, or if you gave a look to the slides, let's say, to answer to these questions. Okay, this is just, of course, to make fun. And here you can find the reference. I used the book of Stephen Blundell, and you can see the chapters here that I used. And you will find, of course, all the videos, experiments, and so on in the additional material on the Google Drive or on the site of the Polytechnico. And we will figure out how to share it with the people that cannot access to both of them. Okay, do you have some questions?